Alright, this is the notes for section 8.4, radical notation for nth roots. So really the big idea here is that we want to look at the relationship between these two things. Okay, what we call radical notation and writing a root using a fraction in the exponent. So really for any integer n, the largest real nth root of x can be represented by either one of those. So right now we're going to look at the situation where those two things are really the same. Okay, so when we say the definition of the nth root of x, and that's how we read that, the nth root of x, and we're going to only look at it for right now when x is greater than or equal to 0. For right now, that's all we're going to limit it to. And it says that when x is a non-negative and n is an integer greater than or equal to 2, these two things will be exactly the same. So in other words, 32 to the 1/5 and the fifth root of 32 are the identical value, and they're both equal to 2. Now we know that there are other fifth roots of 32. In fact, we'll find out a little bit later on in this course that there are exactly 5 of them if we account for things in some different ways. But when we're talking about the way we're representing it, with 32 being a positive number, both of these represent the same thing, and that is that positive real fifth root of 32, which is 2. Alright, one application that we have for radical notation is using what we call the geometric mean. Now you're familiar with the mean, which is just the average of a set of numbers. Well, that's just one measure of what we call central tendency. We have several other ones, some of them that you're familiar with, some of them that you're not. This is kind of a new one to you, though. A geometric mean is the following. If you have a set of n numbers, we say that the geometric mean can be found by multiplying the numbers together and then taking the nth root of the product. So we're going to take the numbers, then we're going to multiply them together, multiplying those numbers together, and then once we get that product, we're going to take the nth root of those numbers. So the geometric mean is really good when you have a really desperate or a set of numbers that are very dispersed, and they're good for keeping one really large number from disproportionately affecting the measure of that center. So here's an example of how we might want to use that. So let's say we have the following chart below, shows the population for 8 1 square mile regions in the United States. Use the geometric mean to compute an average population density. So we have these different values, and as you can see, some of these numbers are quite small and then others are very large. So it really will be a way that we can measure the center of that without those large ones affecting it too greatly. So what we would do is we'd take all of these numbers and not add them together but multiply them together. And then once we've done that, we're going to take the 8th root of them. So if I do that here, if I take all of these numbers, multiply them together, and then take the 8th root, you'll notice that I get 1656. Alright, as I mentioned earlier, when we look at nth roots of a number, there's actually, whatever value of n we have within a certain stipulation, we're going to find out that there are that many roots of it. So really the question is, well, what does the nth root of x represent? Well, it actually represents only one number. So when I say the third root of 7 or something like that, it actually represents just a number, and the number that it represents is as long as x is positive and n is even. And that's kind of the limitations that we're putting on this at the beginning. As long as n is even and x is positive, x has 2 real nth roots. But only the positive real root is denoted by the nth root of x, which is exactly the same as x to the 1 over n. So when we are talking about when we have 2 real nth roots, which happens when it's even, we're saying that both of these only represent the positive nth root of x. Okay, it doesn't represent all of them. We're going to find out that there are ones that are complex or imaginary numbers. We know that when it's even, there's going to be two real ones, and when we say the nth root of x, or we say x to the 1 over n, we're only representing the positive real nth root of x. All right, let's take a look at this next example here. It says, find all fourth roots of 16. Now, in other words, what that really means is solve x to the fourth equals 16. Okay. Once we do that, we want to know which one does the fourth root of 16 represent, and which one does the 16 to the 1/4 represent. So when I say the fourth root of 16, really I'm saying, what number can I raise to the fourth power and get 16? Well, I know from chapter 7 that if I take 2 to the fourth power, that is equal to 16. So if 2 to the fourth is 16, well then negative 2 to the fourth, because we're talking about an even power, must also be 16. So there are my two real roots of 16. Now, there are also two other ones. Okay, now we can, right now we don't really, I mean, we could use technology to do this, but if we think about it a little bit, I think we can get there as well. If I think about 2I to the fourth power, well, that's also 16, because if you think about what 2I, that's really 2 to the fourth times I to the fourth, and 2 to the fourth is 16, and I to the fourth is like I squared times I squared, and we know that I squared is -1, so it's really like 16 times -1 times -1, which is equal to 16. So 2I to the fourth is also 16, which would also mean that negative 2I to the fourth would be 16. So we actually have four fourth roots of 16. Well, which fourth root of 16 does the fourth root of 16 represent? So when I write it like this, what does that represent? Well, that represents only the positive real one, which is 2. Now, that's also the exact same one that this represents. So this is exactly the same thing as it relates to a fractional power. The last new concept that we have here is the root of the power theorem, and what it does is it digs a little bit deeper into the relationship between writing things in radical notation and writing things in fractional powers with fractional notation. So what we're really looking at is the relationship between something like this, which we looked at back in chapter 7, and how does that relate to radical notations? Well, it turns out that it's exactly the same as the nth root of x to the m, or the nth root of x to the m written like this. Either one of those is the same. So in other words, it doesn't matter if I take a root or a power first, just like we learned in chapter 7. It also doesn't matter which way we write it, as long as we know that we're looking at x values being positive, and we know that m is greater than or equal to 2 and n is greater than or equal to 2. If those things are in place, then we are good with saying that these two things are exactly the same. So really, if you think about this lesson, as long as we have those stipulations in place about x and about m and n, writing things fractionally and writing them in radical form really mean the exact same thing. So let's take a look at this last example. It says rewrite the square root of the square root of the square root of the square root of 10 using rational exponents. Is this expression an nth root of 10? Justify your answer. So if I were going to take this and rewrite it in with a rational exponent, or in other words using fractions, remember this is like the square root of the square root of the square root of the square root. Okay, so that's really like saying 10 raised to the 1/2 power, raised to the 1/2 power again, and then finally a fourth time. So I'm really taking 10 and raising it to the 1/2 power 4 times. Well, it's a power of a power of a power. In other words, each one of these, I'm going to take these values and I'm going to multiply them together. So it's really like saying 2 to the 4th 16th, which would be the 16th power. So it's really like saying 10 to the 1/16th power if I were going to write it using rational exponents. And that's exactly what we would have here, which means that it's also equal to the 16th root of 10. So those two things are exactly the same. All right, the last part of this question asked us to justify our answer. So if we got to justify our answer, really what we're saying is if I were to take this and if I were to raise it to the 16th power, it should be equal to 10. So let's do that. If I take 10 to the 1/16th of 16th and raise it to the 16th power, well, if I'm doing a power of a power, that's just multiplication. So 1/16th times 16, which is just 10 to the first power, which is equal to 10. So the answer is yes, it would justify that.